Okay, and so welcome everybody this afternoon. Our speaker is Yaiza Canzani, and she will talk about eigenfunction concentration via geodesic beams. Please.
Thank you so much. Thank you for the invitation to speak here. What I'm going to do is I'm going to give a talk, as I was saying, that's related to a series of projects on which I've been working with my collaborator, Jeff Galkowski. We developed this framework to try to understand how eigenfunctions concentrate on a manifold. And we have been applying this framework to study different problems. So I'm just going to discuss a couple of them, a couple of the applications here. I will describe the framework and then the applications, and hopefully you will interrupt me as you have questions. I would appreciate if you do that. Okay, so here we go. Let me explain what the setup and the motivation for the talk is first. So we are gonna work on a manifold that's gonna be compact, smooth, and it will have no boundary. Now, because we are gonna be talking about concentration of eigenfunctions, I'm gonna be giving you tons of bounds for growth, for eigenfunction growth. And these bounds are usually expressed in terms of the dimension of the manifold. So throughout the talk, the dimension of the manifold is going to be n. So just remember that. The manifold is compact. So when you think of the Laplacian acting on the manifold, its spectrum is discrete. It's formed by eigenvalues that are accumulating at infinity. And what we are going to do is we are going to denote the eigenfunctions by phi lambda, and the eigenvalues are going to be lambda squared. So the eigenvalues for the Laplacian are all positive, and we are going to be denoting them as lambda squared, because what happens really is that in all the bounds that I'm going to be discussing, what's driving the behavior is not the eigenvalue itself, but its square root. So I'm going to be mostly working with lambda alone, and I'm going to refer to this as the frequency of the eigenfunction. So lambda squared is the eigenvalue, the frequency is lambda. And because I'm going to be discussing this concentration properties of the eigenfunctions, we need to normalize the problem somehow. And what we are going to do is we're going to ask for the total atom mass to be 1. Now, what this allows you to do is to think of the modulus squared of your eigenfunction as a probability density. So if you think of the modulus squared at the point x, then you're thinking of the probability for finding a quantum particle of energy lambda squared at the point x. The reason why I'm saying this is to motivate the next picture, which is trying to convince you, or at least that's going to be my goal, that the eigenfunctions can reflect the behavior of the dynamics of the background geometry that you have on your space. So here on the left column, I have a disk and I have a cardioid. In red, what you see is the billiard trajectory of a classical particle. So you just started, you kicked your particle with some initial velocity and it starts bouncing around. That's the red trajectory that you're seeing. For the cardioid, here you have the same, only that it ends up filling the entire cardioid because the dynamics are very chaotic. These plots here are plots for eigenfunctions. So in each of the two manifolds, you have 4 eigenfunction plots. The eigenvalues are growing in this direction. And what you're seeing is the density plot. So you're seeing the modulus of the function plotted. Black means the function is concentrated there. White means there is very little of a function where you're looking at. So for example, here, or here, or here, or here, the probability for finding your quantum particle is very close to 0, which mimics what's happening with the classical particle that's not entering this white circle in the middle of your disk. So what this eigenfunction is telling you is that for this state, your particle is going to be constant. The probability for finding your particle, it's going to be big only near the boundary of your disk. In contrast, what happens here for the cardioid is that the eigenfunctions, as the eigenvalue grows, look like they are becoming evenly grayish. And the way in which you should think about that is that if you set here an area that you're interested in studying, what's going to happen is that the probability for finding your quantum particle inside this region is going to be the area that you're looking at. It doesn't matter what the shape of your region is, where the region is located. what happens is that if this is truly evenly grayish, then all what matters in dictating what's the probability for finding your particle is the area of your region. This is what's called quantum ergodicity. So basically what I'm trying to do with this picture is to show you how eigenfunctions can reflect what's happening with the actual flow on your manifold. Basically that's the idea for the entire talk. We are gonna be fixing a point on the manifold, and we are gonna try to understand what's the behavior for the value of a function at the point in terms of what happens with the dynamics of the geodesics that are running through that point. Okay, so I'm gonna first explain what are the types of concentrations that we are gonna care about. We are gonna look first at pointwise bounds, so fixing a point and trying to see how large the function can be at that point. So here what we have is a result that was, many people worked on this result. These are the first two, and this is and Hormander is the one that worked on it in the fullest generality, in the one that I'm stating. And it says that if you look at the modulus of your eigenfunction, it can grow at most like lambda to the n minus 1/2. N is the dimension of the manifold, times a constant. And that constant is going to be uniform for the entire manifold. So it doesn't depend on the point that you're choosing. That's what this result says. And so it tells you how large the eigenfunctions can be. And it's actually saturated. The equality happens for the sphere, for the round sphere. And the eigenfunctions are called zonal harmonics, the ones that saturate this down. The zonal harmonics, if you look at the density plot, so the plot of their absolute value, they peak at the north and south pole, and the height of this peak is exactly like lambda to the n minus 1/2. However, what happens here on the sphere, and I'm gonna try to convince you of this through the entire talk, is that the sphere has enough symmetries that the geodesic flow is quite rigid, and what happens is that any variation of a geodesic that joins the south pole with itself, say, will also give you a geodesic that's closed, and that turns out to be the enemy for this problem. So if you want to saturate these upper bounds, you really need to look like a point on the sphere, basically, from the point of view of the geodesic flow. Now, this is an L infinity bound. You can look at more refined bounds and ask what happens with LP norms. And what happens for LP norms, if you're working with P's that are large enough, so this is the critical exponent, if the values of P that you're looking at are above the critical exponent, then there is this bound that Zhu saw from 88 that says that the LP norms of your eigenfunctions are going to be controlled by the same thing that you had before, corrected by this M/P. In particular, when P is infinity, you recover the L infinity bound that I first stated. Again, this is saturated on the round sphere, but both these bounds are believed to be much better for most geometries. Now, the last topic that I'm gonna introduce and for which we are gonna apply the results that we built is that of counting eigenvalues. So we are gonna be talking about bylaws, and so we are gonna fix a number, lambda squared, and we are gonna count the number of eigenvalues that we have below that threshold that you chose. And what happens is that it's known that the number of eigenvalues that are smaller than lambda squared grows like lambda to the n. And there is an error term. And there is a ton of literature dedicated to trying to improve on this error term, depending on which geometric setup you are in. Mostly the improvements are of the little o type. I'm gonna discuss this later. But what we are gonna be doing in this talk is in general, try to get quantitative improvements on these three bounds. So we are gonna impose conditions on the dynamics of the flow, on your manifold that will give you quantitative improvements for all these bounds that are known to hold always. Okay, so what I'm gonna do now is I'm gonna describe what the structure for the talk is, and then I'm gonna start going over each of the pieces. So this is the structure. I'm gonna first discuss how you can decompose eigenfunctions.
May I ask you a question?
Please.
So in the while law, the correction, what does it depend on? Is there some explicit geometric quantity that it depends on?
Yes. So depending on what your setup is, how much you can say, the most is known when you're working on domains in the plane with a boundary that's smooth. And then the error term depends on the length of the boundary and on the curvature of the boundary. For when you don't have a boundary, then this error term depends on the curvature, but it's not explicit the way in which it does depend. And really, depending on the geometric setup you're in, there are some results like that gives you good error terms for the torus, for the sphere, but it's quite hard to actually pin down how it depends on your geometry, depending on the manifold that you're in.
Okay, thanks.
Okay, so the first thing that we are going to do is to talk about how to decompose eigenfunctions into superpositions of geodesic beams. So these geodesic beams I'm going to introduce, and I'm going to explain how to think of the eigenfunction as decomposed into these new functions, these pieces that we are calling beams. Then what I'm going to do is to explain how to control the value of the function at a point in terms of these beams that I will introduce. Then we are going to talk about how to improve on pointwise bounds, how to improve on LP norms, and how to improve on Weil laws. So basically what happens is from here to the end of the talk, there are only 5 slides, and each slide is one of these topics. And I'm going to start here explaining what the framework that Jeff Kalkowski and I created is about. So let's do that. The first thing that we are going to do to decompose the eigenfunctions is to fix a point. And then you're going to look at all the directions in which you can move from that point on. In the space of all directions, which is here, the I work in the cotangent bundle because the techniques that we use come from semi-classical analysis. And this is the cosphere fiber at X. So that means this is your point X, and you have a circle of directions that emanate from X. The notation that we use is X for the foot point, C for the covector for the direction, the momentum if you want. What we are going to do is we are going to cover the set of all the directions that emanate from X with balls of radius r lambda. So basically here you have the circle of directions, you're covering it with balls of radius r lambda. This r lambda, as you can see, is like lambda to the minus a half. So it's going to 0 as lambda grows. So the radius of these balls are shrinking to 0. And what you're going to do with these balls is you're going to turn on the geodesic flow, and you're going to propagate them for a finite amount of time. So you're going to create these geodesic tubes that have fixed length, but the head of the tubes are these balls that are getting narrower and narrower as lambda grows. So think of this as very thin needles. That's what you'll end up working with. And what we are going to do is to localize your functions to each of these tubes. And then we are going to try to control the value of the function at the point X by understanding what happens with the restriction of the function to each of these tubes and how these tubes evolve under the geodesic flow. That's the main idea. So I'm going to explain now how that's going to be done. So this is the same picture I was showing you, only smaller. What we are going to do is we fix the point, and near the point X, we are going to decompose the function. So this is only a local decomposition, and it's going to look like this, like a sum of pieces. These are my geodesic beams. So what is each of these pieces? So basically what we are doing is we are looking at one of these tubes that we just built. This is a tube TJ. And then we are localizing to a tube using this operator that I'm denoting by KTJ. So what is this operator really? This operator is the quantization of a symbol whose support is inside my tube. So let me explain that. This KTJ that's appearing here, it's this operator that I'm thinking of as the quantization of a symbol whose support is inside my tube in frequency space. So basically what's happening is, if you're not familiar with quantization procedures, what you're doing is you are using this function, KTJ. This is just a function that's defined in phase space. And it's a cutoff function, a smooth cutoff function to the tube that you built in phase space. And then what you do is you turn it into an operator. What is this operator doing for you? Well, what it's gonna do is it's gonna localize your function in position near the point X where you are working, but it also localizes the function in frequency to the tube that you're looking at. What do I mean by that? What I mean is, like, if you take the Fourier transform of each of these pieces, then that Fourier transform, which is a function of the frequency only, of C only, it's supported inside this tube. That's how you should think of it. So you should think that this operator, what it's doing for you is it's localized, this new function, this geodesic beam is localized near the point X, and its Fourier transform in frequency is localized to the tube to which the KTJ is associated. So basically, each of these geodesic beams is only keeping track of the information that pertains the function in the direction that you chose to build your tube. And they are not built just in a random way. The way in which these are actually built is so that each of these geodesic beams, each of these pieces, behaves like a solution to your eigenvalue problem. So your full eigenfunction phi lambda satisfies the equation Laplacian minus lambda squared phi lambda is equal to 0. What these geodesic beams satisfy is that they are going to be approximate solutions for your eigenvalue problem. And really, the reason that's behind asking for our tubes to be centered around geodesics is demanding that this property be true. Basically, what's happening here is you're looking at this operator, and you're asking for them to commute at least to first order, because your eigenfunction is an eigenfunction of this one. So you want to use that. But for these two operators to commute, at the level of their principal symbols, what you're asking is that this cutoff function that you're using to build the cutoff operator has to be invariant under the geodesic flow, which is the flow for the principal symbol of the Laplacian. So this is the reason why our tubes are centered around geodesics. And that's the main picture. So you fix a point X, and near the point X, you decompose the function as a sum of these pieces, each of which look like an approximate solution for your eigenvalue problem. And it's localized in a tube that you control a lot, because you're just fixing a direction in which you're going to be leaving the point, and you only look at what happens with your function in that direction. And when I say what happens with your function, I mean both in position, but also through its Fourier transform in momentum. And so that you have a picture of how these pieces look like. If you were to...
If the equality is only local, is it only phi lambda restricted to a neighborhood, or?
Yeah, it's only, yeah, so this decomposition only works near the point X. And you cannot have a global decomposition unless you are on the sphere. So something funny that happens on the sphere is that you can actually build these beams, and they are going to be exact solutions for your eigenvalue problem. They are called, these geodesic beams on the sphere, they are called Gaussian beams, or also they are known as highest weight spherical harmonics. And they are concentrated in a tube like this, but they are actual global solutions for your eigenvalue problem. So for them, yes, you can use them to do global decompositions, but for our purposes in general, you should think that this is only local, very local. And actually, so if you want to picture how one of these beams would look like, you should have this following image. So you pick this direction, which is the one that's highlighted here. And then along that direction, you have this tube. The width of the tube is r lambda. And then running along that the direction that you chose, you have your eigenfunction, which looks like a ridge along your geodesic. And the height of this is just the value of the function along the geodesic. For the highest weight spherical harmonics, so for these Gaussian beams, this height is like lambda to the 1/4. And the radius is exactly lambda to the 1/2. So on the round sphere, you have these eigenfunctions that concentrate along the equator, any closed geodesic really, and they look like this. They look like they have this big bump along the equator, and outside the equator, they decay super fast. They are exponentially small outside a band of radius lambda to the -1/2, sorry, around the equator. And this is only one beam, but if you start using combinations of beams through a point, then you can start building functions with different shapes. So for example, suppose you choose two beams that are orthogonal to each other, then what's gonna happen is that they are gonna cohere at the point where they intersect, and then your function is gonna look like a bump. And the more beams that go through that point you have, the highest the value at the bump is gonna be. So for example, if you want to recreate what happens with the zonal harmonics, these eigenfunctions that were saturating the universal bounds for the L infinity norm, then what you need to do really is to put as many beams through the point as you possibly can while still keeping them orthogonal to each other. What happens is that if you're trying to do this, you realize quickly that the maximum number of beams that you can put through a point while still keeping them orthogonal to each other is related to the width of the heads of these tubes. So if this is like lambda to the -1/2, the radius of that ball, then you can fit exactly lambda to the 1/2 beams through the point while still keeping these beams orthogonal. And that's exactly the makeup of a zonal harmonic on the sphere. A zonal harmonic on the sphere looks like you just put lambda to the 1/2 beams through the north and south pole. And these beams are adding up together at the point to create a peak. And that peak that you're creating has exactly height lambda to the -1/2, like the universal upper bound. So in terms of this beams decomposition, any function that saturates this subnorm bound is actually going to look like this. It's going to have a positive measure set of directions in which you're arranging as many beams as you can possibly fit in that positive set of directions. And that's going to be giving you the growth that's going to look like exactly what you got for the upper bound. And in general, the idea for this is that we wanted to control the value of the function at the point x. And what we are going to do is to control it in terms of what each of these pieces, what each of our geodesic beams are going to do under the geodesic flow. So now you have like these tiny tubes here, and you're going to turn on the geodesic flow, and you're going to start checking if these tubes are going to end up wandering around and never coming back, or if they actually are going to be tubes that come back to themselves. If that happens, then those tubes that do look back, like what happens for all the tubes on the sphere, are going to contribute to give you a higher value for the function at the point. If the tubes wander around, then those tubes are going to end up dissipating mass, basically. So that's the content of my next slide. I'm going to try to explain how you control the value of the function at a point x in terms of what these tubes are doing for you.
Excuse me, just one question. So this I, in general, how big should I think that the index set of your J's is? How many Gaussian beams or geodesic beams are you going to use?
Perfect. So let me answer it for surfaces because it's easier to see. Then what happens is that if you're looking at how many beams at most you are going to end up fitting while still keeping them orthogonal to each other, the radius of each of these tubes is like lambda to the minus a half. It's very small. So you can fit at most lambda to the 1/2 of them. So that's the number of beams, that plus times a constant that only depends on your manifold is the number of beams that you're going to be using at the most to decompose your function. And in general, for general dimensions, it's lambda to the n minus 1/2. Yeah. Okay. So let me explain how to control the value of the function at the point x. Basically,
can you say maybe what happens, say, if you're in a nodal point? Like, do you have decoherence of these? Like, what? How does this picture look like when you?
No,
when you don't try to capture the maximum, but rather the minimum of the absolute value.
I don't think these tools are sensitive to detect zeros of functions. They can detect properties like growth, but not like changes of sign.
No, but I mean, if you have like, can you capture the decoherence? Because it's you'll be in a point where you have all the directions, only they somehow cancel each other. Is this something that?
Oh yes, I mean this will detect like yes. It's easier to see it when, like, for example, you have if you have a symmetry that's apparent with respect to the point or with respect to a submanifold, then yes, I mean in principle you could read that symmetry from the decomposition. Yeah, like you really are reconstructing the function from the beams. The thing is like whether you can actually work with your decomposition or not, depending on the geometric setup that you have. So the idea is the following. You're looking at all the directions that are leaving your point, and you're gonna think of them as either good or bad directions. Bad means that you can back to loop on yourself. And good, and that's green in this picture, means that those directions are gonna end up wandering around and not coming back for times that are logarithmic in lambda. So that's the time scale that I'm interested in. And we are only gonna look for the eigenfunction phi lambda up to log lambda time. And basically what we do is we are fixing a point. We are decomposing the family of tubes into two collections, the good and the bad tubes, where good means that the family of good tubes is such that it's non-self-looping for time log lambda. So this family of tubes, when you evolve it under the geodesic flow, it doesn't come back to self-intersect in phase space before time log lambda. That's what good means. If you can manage to have this splitting, and you can in many cases, as I'm going to explain in the applications, then what happens is that the bound for your eigenfunction looks as follows. So for a second, forget about this bit. If you remove this bit, then you just get exactly what Hormander's bound looked like. It's a constant times lambda to the n minus 1/2. So now what we have is this universal bound that we knew holds, but it's weighted by this factor. So what one hopes is that this factor will give you a quantitative improvement. So let's parse what this factor has in it. So you have the number of bad tubes to the power of 1/2, the number of good tubes to the power of 1/2. The number of good tubes has this improvement in it. It's divided by log lambda. And then everything is multiplied by the radius of your tubes to the power of n minus 1/2. So one way in which you can think of this really is if you combine these two together, it's going to give you the volume of the set of bad directions and to the power of 1/2. The reason for that is that if you only look at a single tube, this tube, the head, has radius r of lambda. And remember, this is a head that lives in the co-sphere fiber at x. So this is a space whose dimension is n minus 1. So that means that the volume of this tube, whose length is fixed, the length of the tube has no role here. The volume of a single tube then is gonna be r to the n minus 1. So what you have here is the volume of a single tube to the power of a half. And when you multiply that by the number of bad tubes to the power of a half, you get the volume of the set of bad directions to the power of a half. So really the way in which you should be thinking of this weight in front of the universal bound is that here these two combined give you the volume of the set of bad directions that emanate from the point, and these two combined give you the volume of the set of good directions that emanate from the point, the square root of that, but with the logarithmic improvement. So what you're gonna hope is that you can do a decomposition into good and bad tubes in such a way that the number of bad tubes is small enough so that this term is really driving the growth. And then you would get a logarithmic improvement over the universal bound. That's the idea. You just hope that you have a decomposition into good and bad tubes, and that for some reason the geometric information that you have of the geodesics running through the point X is gonna allow you to say, oh, okay, most of my tubes are good for logarithmic times, and then I'm gonna get this logarithmic improvement because this term is just gonna be too small in comparison. So what I want to do before actually explaining how one goes out out checking an assumption like this or the setups in which you can actually work with it, is to tell you where this result comes from. And it comes from the following bound that works under no assumptions. And what it says is that you can control the value of your eigenfunction at the point X by the following. So here, this is the universal bound that you had before, the same radius. But now, instead of having number of good tubes and bad tubes, what you have is a sum of L2 masses. And the L2 masses that you're adding up are the L2 masses for each of your beams. So you're localizing your function to a tube, and you're just measuring the L2 mass of that restriction to the tube. And then once you add all the L2 masses, you have your weight in front of the L infinity norm. So basically what happens, you should think, is that in general, for the universal bound, this term is not there, and this sum adds up to roughly 1. What happens is that you can get this R of lambda improvement here because of the following reasons. And this is like a 3-bullet point sketch of a proof. Each of your beams, this is what I'm denoting by beam, has its Fourier transform supported inside a tube. So the Fourier transform of this beam is inside one of these tubes. And what that means is that if you're looking at the geodesic tube, you have your geodesic, you have the tube around the geodesic, and this has, the head of the tube has radius R of lambda. So what happens is that if you look at the normal direction to the geodesic, that's what I'm denoting as xi nu here, that normal direction in length is gonna be smaller than R of lambda. And if you are in the support of the Fourier transform of your beam, localizing the function to the tube exactly says that your frequencies are gonna be localized to this tube. So the normal component of your frequency is gonna be bounded by R of lambda. And the way in which this helps you is because if you now take normal derivatives to the curve, to the geodesic, then these normal derivatives are gonna come with an R of lambda improvement. Basically, if you take alpha derivatives in the normal direction, then you're gonna get an R of lambda to the power of alpha improvement on the L2 norm. And then if you have a better control of the derivatives, like in this case, you can use a solo estimate to just control the L infinity norm in the normal directions, because you can control the derivatives in the normal directions. So you can use a solo estimate to get this R of lambda to the N-1 improvement. And then in turn use it to get this extra term here for the bound. So that's basically the idea. The idea is that the localization of your functions to the tubes allows you to get this R of lambda improvement that's picking up the volume of a single tube for each of these terms. And this is quite helpful because then if you didn't have this term, then this would not be here, and you couldn't actually work with this as if it was volumes of good tubes, volumes of bad tubes. It really is helping the estimate. And the reason why you can go from this sum to this term here is the Gorip's theorem. So the way in which you go from norms, L2 norms of eigenfunctions, well, not eigenfunctions, the L2 masses of the beams to getting these logarithmic improvements is simply the fact that, well, if you grab a single beam, then the L2 mass of that beam is controlled by the total mass of your function. This doesn't say much. It just says that if you restrict your function to a tube, you get something smaller in L2 than the total function. But then you can use the Gorip's theorem to do the following. You can be like, okay, my single beam is supported on this tube. So then what I can do is to propagate my tube once. And then you end up with this new tube. And this tube doesn't self-intersect if I'm working with my family of green good tubes. I know that this tube is not self-intersecting. And under that assumption, what the Gorip's theorem tells you is that then the L2 mass on this new tube is twice the original L2 mass. So you get this lower bound here now. I mean, on the one hand, you know that the L2 mass on this entire tube is controlled by this. And on the other hand, Gorip's theorem tells you, well, but because the tube is not self-intersecting, the mass of these combined tubes is twice the original mass. So then you have this bound, and you can run this argument for as long as your tubes don't come back to intersect themselves. So if you run it 3 times, then you get a 3 in front. If you run it for logarithmic times, so for one of these tubes here that were not self-looping 4 times log lambda, then you get this log lambda improvement in front. And this is how, for each of these beams that were good, you get the L2 mass, the total L2 mass divided by log lambda, which is what appears here. So for the good tubes only, you get this logarithmic improvement. That's an outcome of the Gorip's theorem. And this also explains why I'm using log lambda. So what happens with the Gorip's theorem is that it only works up to Ehrenfest time. Ehrenfest time it's like log lambda, it's logarithmic in lambda. And so if you're working on a general manifold and you only know that it's compact and smooth with no boundary, then you can only run this theorem. You can only keep track of what happens with propagations of your masses for logarithmic times. If you were working in a setup where you have control of what happens under the geodesic flow for times that are longer than log lambda, like say for polynomial times, then you have something better than a logarithmic improvement here in this bound. But in its fullest generality, only log lambda we can put. And what should I say? Perhaps now it's a good time to actually mention that these results, they not only hold for eigenfunctions, they also hold for quasimodes, so approximate solutions for the Laplacian. And also not only for the Laplacian. These results, we prove them in way more generality than that. We prove them for pseudo-differential operators that are elliptic and self-adjoint. If you have those 2, elliptic and self-adjointness, then you can restate all these results for eigenfunctions or quasimodes of those operators. The only thing that you have to do is, instead of working with the geodesic flow, you need to work with the bicharacteristic flow for the principal symbol of your operator. So your tubes are built around bicharacteristic lines rather than geodesics. The reason why I choose to give this talk for the Laplacian is because you can picture the geodesic flow much better than just any bicharacteristic flow. And it's easier to talk about this because we have a link already established between the geometry of the manifold and the geodesic flow. Okay, so what happens with the improvements on pointwise bounds is that this bound that was due to Hormander was improved by many people to a little low upper bound. And in terms of quantitative improvements, was only improved by Verard. And the improvement is like square root log lambda. And it worked under the assumption that you should have no conjugate points. Now, this assumption is an assumption on the entire geometry of your manifold, and it's quite strong. What it says is that if you have any two pairs of points, x and y, that are joined by a geodesic, then no matter which variation of this geodesic you choose, geodesics need to be spreading apart in that direction. So basically, if you look at variations in a direction that's given by a Jacobi field, that's a solution to this equation, then what's going to happen is that the new geodesic is going to wrap around the old one. And you were forcing your Jacobi field here to vanish. That means that the two geodesics start at the same point. But once you get all the way up to the other point, your Jacobi field has a is not zero. So J of y here is different from zero. So that's making the two geodesics spread apart from each other. So basically, having no conjugate points, what it means is that for any two pair of points that you have, geodesics are going to be spreading apart in every direction, in every direction that you can think of. If these 2 points are connected by a geodesic, any variation of that geodesic is going to yield a new geodesic that's spreading apart from the original one. And this is a very strong condition. And in the opposite case to this condition, you have the round sphere. For the round sphere, if you start with a geodesic that closes, then this point is going to be conjugate to itself, for example. If you consider any variation of this geodesic, this variation is going to give you a new geodesic that's going to wrap around and come back to close. So what happens on the sphere is like the exact opposite of this picture. Every point is conjugate to itself, but it's also conjugate with maximum multiplicity. What that means is that in every possible direction, all the geodesics are coming back to close. If you force your Jacobi field to be zero here, then upon return, the Jacobi field also is forced to vanish on the sphere. Now, between these two geometric setups, you have a wide range of cases, right? Like you may have 2 points that are connected through geodesics, and in some directions, geodesics are spreading apart, and in some geodesics are actually staying put. So what we were able to do is to get this logarithmic improvement for that range of cases in between. And basically, the assumption that we are asking is that if you're starting at a point here, and you return after time t to the point, exponentially close in time to the point, then what you need to ask is for not all the Jacobi fields to vanish upon return. So what this is telling you is that if you happen to be at a point for which the geodesics are going to return, then upon return, there has to be, the geodesics are going to be spreading at least in one direction. There has to be one direction in which geodesics are going to be spreading apart. And basically, what we do is to use that direction to build a set of good tubes that are not going to be self-looping. If you have that one direction in which geodesics are spreading apart, we can get the logarithmic improvement for the n-infinity norm in a ball of center x and radius r lambda. R lambda is going to 0. And so we recover this result, but in this much more general setup where we are asking that there has to be one direction in which things are spreading apart. The existence of one such direction is enough for us to get the logarithmic improvement.
Is this hyperbolicity? Is this like demanding for hyperbolicity?
You don't need hyperbolicity. That's what's nice. So
some
this is
kind
only
of like
a condition. Sorry?
It's kind of like a Nosov.
Well, if your manifold was a Nosov, this would be satisfied. If the manifold has no conjugate points, this is definitely satisfied. But this is even stronger than that, because you're only looking at what happens at the point x. And with geodesics that run through the point x, you don't care what happens with the rest of your manifold. You are only looking at the behavior of those geodesics that join the point x with itself. And if for each of those geodesics you have one direction in which things are spreading apart, then you're good to go and you get this logarithmic improvement. That's the idea. Is that okay?
Do you have a non-trivial non-trivial example where it's not like this? which is not a sphere, not something which is maximally self-conjugate?
Poles of surfaces of revolution, solid manifolds.
Okay.
But no, you need a lot of symmetries in order for all your geodesics to be very stable under perturbations. Yeah.
Thanks.
Maybe I'm confused with the definition of this not uniformly maximal self-conjugate, but somehow the way I heard you say it was that one direction where things did not come back was enough to gain this square root logarithm improvement. And somehow on the previous slide, you had this sort of, you needed a certain proportion of them to be
no,
good.
So what happens is that if you have one direction in which your geodesics are going to be spreading apart,
yeah.
that one direction is going to generate a positive measure set of tubes that are going to be non-looping because it's an open condition basically.
Okay. Okay, thanks.
Okay, and then I mean you can use this result to get improvements on LP norms. This was the bound that was due to solve. It was improved by Hassel and Daisy in the setup in which you have non-positive curvature. It was improved to a square root log lambda bound. And what we were able to do was to improve it in the same way as Hassel and Daisy, but under a much weaker assumption, which is exactly that if you're working on your surface and you're interested in what happens here inside a subset U of your surface, any manifold, any dimension works. I'm just saying surface to make the drawing. Then what you need to know is that for any pair of points in your subset, the point X cannot be maximally conjugate to Y in exactly the same way that I was describing before. If the point X is joined with the point Y by a geodesic, then there has to be one direction in which things are spreading apart. If you have that, then you can get this logarithmic improvement. So like notice that this is an assumption that's weaker, not only because it includes this setup, but also it's only about what happens with pairs of points that are inside the set in which you're studying the LP norm. You don't need a blanket assumption on the entire geometry of your space. And there are two nice things that came out of this result. The first one was that if you're going to saturate this upper bound, you can only have finitely many points at which the saturation is happening. And also what we can do is to say that at each of those points, really your function is going to look like a zonal harmonic. So the zonal harmonic was the one that had these peaks at the north and south pole. Well, it turns out that if you saturate the LP norms, you have finitely many points in which the saturation is happening. And at those points, you really look at like a zonal harmonic in the sense that your beam decomposition is going to be full of beams in every direction. And these beams are going to look like they look exactly for the zonal harmonic on the sphere. Okay, and for this last layer, this is the one on Weyl laws. So the idea was to improve on the remainder term for the Weyl law. And what's known is by Hormander that the error term grows like lambda to n minus 1. You can improve on this if you ask for your manifold to be aperiodic. This is a result by Doistermat and Guillemin that says that if you look at the set of directions that give you closed geodesics, if that set has measure 0, that's what it means to be aperiodic, then you can get this big O bound down to a little low one. Then recently, Yusevich and Wyman proved that you can actually prove that a product manifold, if you have a manifold that's a product, a non-trivial product, then you can think of, you can prove that it's aperiodic. That's what they did. And then in turn, because of Doistermat and Guillemin result, you can get that for product manifolds, the error term is little low. In terms of quantitative improvements, the only thing that was known was, unless you're working on very rigid cases where computations can be made explicit, is that for manifolds with no conjugate points, you can get a logarithmic improvement on the error term. And this is due to the same work that I was referencing earlier for the subnorms yields that the error term in the count for the eigenvalue counting function gets a logarithmic improvement if you ask for no conjugate points. So what you can do is to grab everything we did before for eigenfunctions and apply it to understanding the number of eigenvalues. There is a relationship between these two problems because you can reduce counting eigenvalues to understanding how what's called spectral projectors work. These are like, how can I explain this? These are linear combinations of eigenfunctions whose eigenvalues are in certain windows. And if you understand how those work, then you can infer how eigenvalues are growing. And basically what we were able to do was to show that if you're working, for example, in a non-trivial product, then you can get the logarithmic improvement without any other assumptions. So a non-trivial product not only is aperiodic in the sense that all closed geodesics have measure 0, but it's actually aperiodic in a stronger sense that allows you to get a logarithmic improvement. And the reason why this result is true is because of a more general result. And this is the last one that I'm presenting. And that is that under an assumption that talks about the volume of the set of directions that are near periodic, you can get the logarithmic improvement. So the assumption is the following. Think of R as a very small number that's going to 0. If you look at the set of directions that are close to being periodic, are close to being periodic for times that are smaller than log of 1 over R, if the volume of such directions, the ones that are near periodic, is bounded by 1 over log R inverse, then, then you get this logarithmic improvement here. So you can get an improvement on the Bayes law as long as you control this. And understanding what's the volume of set of directions that are near periodic can be done in many setups, in particular for product manifolds. It can also be done for manifolds with no conjugate points. And it can be done also in intermediate regimes, as I was talking before. So now that we have this new way of controlling Bayes remainders in terms of the use of these Gaussian beams. Okay, that's it. That's the end of the talk.
Thank you. Questions?
Already asked many.
So how? Yeah, well, you already got many. So maybe you mentioned, but so how optimal are these logarithmic improvements?
I always get asked this question. We don't know. You
don't know?
No.
Could it be a power actually that you're improving?
Could be.
So
yeah, in the last, this wasn't the last conference, but I think it was a couple of conferences ago, I gave this talk and Peter Samak was there. And someone asked exactly this question and he was like, isn't math frustrating? We just have no clue when this upper bound is saturated. The truth is, we just don't know.
Yeah.
Yeah, we don't know if we can, I mean, there are many cases in which one can improve, but in general, we don't, at the moment, we don't have a good feeling for what the best bound is.
I mean, even if you assume, for instance, I don't know, that the point is so lucky that there's really nothing coming back, for instance, but you know.
No. On arithmetic surfaces, Peter would tell you that you get a polynomial improvement, that's what he expects, but that's about it. We don't know.
But it's not clear, then to me, it's not clear how do you relate to your geometric condition in that case, right? Because your geometric condition might be true for lots of reasons.
Yes, I agree with that. I agree with that. I think what happens in the arithmetic case, though, is that you can actually use this. There is an improvement to this tool that we were using, Gorip's theorem, that allows you to keep track of what happens for longer times because you use that the eigenfunctions are both eigenfunctions of the Laplacian and the Hecke operators. And so that allows you to keep track of what happens with the evolution of the masses for longer times. But I mean, I don't know. In general, I don't know. And we don't know when these bounds are saturated.
How about in the case where you sort of just have the capital O, the Hermander case on your slide? I mean, you somehow know that if all the geodesics have the same period, then you are in this situation.
Yes.
Could you say that if you somehow have large sets but with different periods, that then you could see that there's a positive or a negative cancellation when you come back? Is that something you can control?
I mean, I think if you really knew how geodesics are returning or not, yes, you could use what we did to have better control. What I would expect is that whenever you have a positive even sequence of, like if you think of it as like for different times, you have different sequences of directions that are returning for generating geodesics returning exactly at that time, then that's gonna make the bound be saturated. That's what I believe, but we don't even know that. Like very little is known about how eigenfunctions connects, how the behavior of closed geodesics and their return connects to bumping the eigenvalue. Sorry, the error term for the bylaw. Yeah.
Thanks. I also had a different question if nobody else is. On your slide 2,
go ahead.
I think.
Okay. Trying to get there. It's number 2 or
number 2, not slide 2, but your bullet 2, this one, yeah. So somehow the way you explained the bound, it sounded as if there's this factor r of lambda to the n-1 together with the parenthesis, that it sounded as if a bit as if that should be understood as an integral over the sphere of the directions divided by the return time, and then a square root of that, I guess. Is that really what you get, or is because that?
You can think of it exactly in that way. Yeah.
Okay. Yeah. Thanks.
Well, what happened in this situation if you're sitting on a critical point, where now you have like your Morse index to characterize these balls, now these tubes, now you can characterize them also to good, bad, but also to say to positive or negative or something of this form.
I mean, but you would have to be talking about a critical point for a sequence of eigenfunctions. Like, remember that all these estimates hold for lambda going to infinity, right?
Yeah,
so
yeah, of course. But
looking at a sequence of lambdas, and then your
no,
point
I'm talking about a single eigenfunction. Still thinking about it in terms of the eigenvalue, but then later on some argument about running over all critical points. So if you have something for all critical points of a certain eigenfunctions, and then you have, I'm just trying to figure out like if there's anything.
I don't know. So like what happens is that every time that we apply the result, we do not choose any information about the eigenfunctions themselves. More so what we really use is information about the dynamics of the flow with respect to the point. And then that turns into information about the eigenfunctions. We have not used information about how the eigenfunctions behave at the point that you're interested in. It's more like if you have a lot of geodesics that are coming back to the point X, that's going to bump up the value of the eigenfunction. But we do not think of the other arrow, say.
Yeah, but that's exactly what I'm trying to figure out. If because if we have access to information, you're looking at the critical point. It must have a certain meaning for the dynamics for this point to be, say, a maximum or a minimum, something that should be a point where you have.
It's gonna have information about the masses that your function have on the tubes, but the dynamics are not gonna be impacted by the fact that the point is a critical point for your eigenfunction or not. The dynamics are set from the very start, regardless of the sequence of eigenfunctions that you're looking at.
Other questions? That does not seem to be the case, but you got many today. So thank you for the wonderful lectures.
Well, thank you so much for the presentation.